All right, well, good evening and welcome to lecture number 3 for MT225. Let's see here tonight. We'll be building on what we worked on last time. We started with some of the basic math concepts, and we're going to get a little bit more into some more advanced ideas here tonight that'll set us up for our next big application, which will be working a little bit with vectors. So again, adding and dropping, I think everyone who's online right now is added into the class, but if you still need to take care of that, there's the information you'll need for it. Homework 1 has been posted. So if you go to the class website, you'll find under the homework directory, you'll find the number 1. And underneath there, you'll find a copy of the homework assignment. It's due a week from tonight. If we happen to be meeting in person on that night, then it'll be due at the end of class. If we're not meeting in person, then make sure you scan and email it, or take a picture and text it to me, something by the end of the night. So 11:59 p.m. on 2/17. Let's see here. So the class website, the YouTube channel, and Zoom information, hopefully everyone's been able to gain access to the YouTube channel. I've noticed some views on the videos, so at least they're getting utilized. So hopefully they're useful. And let's move on to what we're working on tonight. Uh-oh. Let's see here. There we go. That's better. All right. So tonight, our big objective tonight, at least the big new material that you may not have seen before, is what we call simultaneous equations. And simultaneous equations is what we have to solve in a typical equilibrium problem. Now, we'll find that throughout most of the course, we'll be able to set things up. If we're careful about how we set our problems up, we can set it up to avoid having to do simultaneous equations, because it's a pretty powerful tool. It's something that does work very well, but it does take a good bit of effort above and beyond just simply solving one equation at a time. If we can set it up to solve one equation at a time, we do, but sometimes we can't avoid it. And when we get into those situations where we need that power, we want to make sure we've got that skill available for us to use. So that'll be what we'll be taking a look at tonight. Older material that we'll be reviewing a little bit tonight also will be a little bit of trig. And so we'll refresh a little bit on the basic ideas of trig. The material covered tonight is on homework 1 as well. The homework assignments always cover the content up to and including the day they were assigned. So you'll find some practice problems on simultaneous equations and on solving trig problems on the homework assignment. So triangle geometry, a little bit of trig review, but everyone who's been through the A&P programs had at least one exercise on it, so we'll review the ideas there. So the big issue here with solving equations is that when we have one equation, all we can handle is one unknown quantity. We saw that last week. We were able to solve an equation if there was only one unknown, one missing piece. But all the problems that we deal with, the realistic and sophisticated problems that we deal with, they don't always involve just one unknown. Sometimes there are 2, or in our course, even 3 unknown quantities. And they're all unknown at the same time. So we can't just find one and then hope we can find the others all the time. We have to be able to solve everything at once. And that's what solving simultaneous equations refers to. Simultaneous means at the same time. So when we solve equations simultaneously, we're solving multiple equations all at once. So when we have a single equation, the most we can handle is one unknown. If we have more than one unknown, we're basically stuck. We can't really solve the equation. And what does that tell us? Well, if it's a math class, it tells us that, well, we can't really do anything. For example, this equation here, 3x plus 2y equals 7. We can't come up with what we call a unique solution to this problem because there are multiple values of x and y that would work. For example, if x equals 1 and y equals 2, that'd work. 3 plus 2 times 2, 3 plus 4 is 7. We could say x is 2 and y is 1/2. That would get us an answer too. Whenever we have more than one unknown in an equation, we have an infinite number of solutions. And that's basically what you'd say in a math class, is that you have an infinite number of solutions. In reality, what it tells us is we need to go measure something. It tells us we need more information. We can't solve this problem right now, but if I can go out there and find a value for x, or find something else that x is involved in and figure out what x needs to be, I can plug x in here and figure out what y has to be. So if we only have one unknown, it means we're missing two unknowns. It means we're missing information, and we need to go find another piece of information. And that other piece of information might be a measurement. It might be another equation that x is involved in. And that's what happens with simultaneous equations. We end up with two equations that both of our unknowns are involved in. And when we have two equations and two unknowns, in most realistic situations, we can solve those equations uniquely. We can get a value for x and y that works in both equations at the same time. If you're a little more mathematically inclined, you might be used to thinking of an equation like the one that's written up here in the notes as basically being the equation of a line. Well, if you have two equations that kind of look like that, what you've got are two lines. In general, unless you're in special situations, two lines will only cross at one point. And in realistic situations, in physical situations, they always cross at one point. We don't usually have parallel lines that never cross, or two lines that are the same and just sit on top of each other. In realistic problems, we always have a point where they cross, and that's our solution. So if we have two equations and two unknowns, that both equations have to be satisfied by those two unknowns at the same time, we can manipulate the equations so that we can solve for both. And there are a number of different methods to do this. If you go further in math and engineering, eventually you'll take a class called linear algebra. And linear algebra is basically all about solving simultaneous equations. Usually it's things like 3 equations and 3 unknowns, or 4 equations and 4 unknowns, or even higher. By that point, you get a computer to do the work for you. But for our purposes, 2 equations and 2 unknowns is going to be enough for our class, and it's not too bad to work those out by hand. And I'll start off with a couple simple examples, and then we'll work on a few more complex ones. And I'll show you some different techniques on how to solve these reliably and quickly. So here's a nice simple equation, a set of equations. We've got x plus y equals 5 and x minus y equals 1. And this set of equations is simple enough that you might just be able to stare at it for a little bit and come up with a couple numbers that work in both. We call that solving by inspection, where you look at it, stare at it for a while, inspect it, and you come up with an answer that works. Now, realistically, we don't have nice coefficients in front of our unknowns, so we end up having to do a little bit more work. We can't really solve these by inspection in practice, but for a simple example, it's not a bad idea to kind of try a couple values and see what works. Maybe by now you've looked at it and you said, well, if x equals 3 and y equals 2, that'd work. And there are no other numbers it'll work for. 3 plus 2 equals 5, and 3 minus 2 equals 1. That is our unique solution. So now that we know the answers, let's use a little more sophisticated method to solve it and see that we get the right answers. So I'm going to go over to the whiteboard here, the white sheet, and write those down. So we have x plus y equals 5 and x minus y equals 1. So let's get those up here. All right, so there are two equations. Back up just a little bit there. So we got x plus y equals 5 and x minus 1 equals y. Now there are a few different solutions, a few different ways to solve these kinds of problems. The method we're going to be using is a method we call elimination. Elimination relies on being able to combine these equations together in such a way that we can eliminate one of the unknowns. And my kind of procedure for this is something I'm going to write off to the side here. And it's sort of generic, but we'll be able to follow it through on some of the examples here. And I'll show you a way that we can make any set of equations into the form we need to make this method work. But the first part of elimination, the first step to elimination is to look for one of your unknowns that has a sign difference. One of the issues I have personally with algebra is I make sign errors. I tend to lose signs. I'd make negatives positive and things like that. So if I can possibly avoid dealing with extra negatives, I usually try to find a way to do it. And I don't think I'm alone in that. I think a lot of people have sign issues that way. So the first thing I look for, because it's going to eventually lead to dealing with fewer signs or messing with signs less, is to look for an unknown that has a sign difference. In the two equations. So for example, here in the equations, we've got x in the first equation, we've got x in the second equation. Both of those are positive. So that doesn't have a sign difference. The sign is the same on x. But with y, we've got a positive y in the first equation, we've got a negative y in the second equation. That's a sign difference. And I refer to that sign difference as built in, meaning that I don't have to force it to be there. I don't have to make it be there. We'll see in some cases we're going to have to make it. We're going to have to make a sign difference. But in this case, there's a built-in one, which means I have less work. The next step is to make the coefficients the same on the unknown with the sign difference, or the unknown you've chosen to eliminate. In fact, up here in step 1, when we look for an unknown that has a sign difference, that's the one we're going to eliminate. That's our target for elimination. So y is our target here. We want to get rid of y. And the way we get rid of y, the way we set it up so that y ends up going away, is we make the coefficients the same. Make the coefficients of the unknown to eliminate the same. And in fact, in this problem, they're already the same. We've got a positive 1y here. We've got a negative 1y here. In our next example, we'll see a situation where they're not the same, and we'll have to figure out a way to make them the same. And I'll show you a relatively quick and easy way to do that. So in this case, we don't really have to do anything for step 2. It's already done. Step 3, this is one that might be a little bit strange if you've never seen this before. We add the equations together. Remember that when we solve an equation, we can do anything we want to the equation as long as we do the same thing to both sides. Yeah, on Monday night, we saw that we could solve an equation, for example, by adding 3x to both sides or subtracting 2 from both sides. As long as we did the same thing to both sides, as long as we put the same value on both sides or we took the same value away from both sides, the equation didn't change. Well, here we've got two equations. X plus y and 5 are the same thing. They balance the scales. X minus y equals 1. X minus y and 1 are the same thing. They have the same value. So if we add x minus y to x plus y on the left, and we add 1 to 5 on the right, we're doing exactly the same thing. We're adding the same value to both sides. We're just writing that value in two different ways. The value 1 can be written as just 1, or it can be written as x minus y. They're the same value. So we add the two equations together. Mechanically, we do that just by dropping the equal sign here. We take the expressions on the left and we add them. So we have x plus y plus x minus y. And if we write that out explicitly here, we won't always write that out all the way. Once you get how this works, it's not too difficult to kind of take a shortcut and get right to your answer. But on the left side, we'd have the left side of the first equation plus the left side of the second, x plus y plus x minus y. On the right, we've got 5 plus 1, that's 6. Now, if we simplify down the left side, this is where the magic happens. If we've done steps 1 and 2 correctly, we'll see something eliminate. Something will cancel out. It'll disappear, and we'll be left with an equation that only has one unknown in it. So let's simplify that here. I can't add x's and y's, but I can add the x's together. X plus x is 2x. But y minus y is 0. The y's have obliterated each other. They're gone. We eliminated y. So we get this equation, 2x equals 6. Well, that's an equation in one unknown. And we can solve for that. All we have to do is lean on our skills from Monday night, solve and x equals 2. What did I screw up here? 2x, something's not right. Because I thought we were going to have x equals 3. So what did I do here? Oh, that's what I did. I did I got ahead of myself in my head here. I wrote down my answer as dividing it. So thank you. Thanks, Evan and Doug. There we go. Missing my whiteboard already. So 2x over 2, 6 over 2. Remember to do the same thing on both sides. So 6 divided by 2, that is 3. See how it helps to know what the answer is going to be before you finish? So x equals 3. So now we've got a value, x equals 3. We've locked down one of our unknowns. So we've added the equations together. That should give us one equation with one unknown. So then we solve that equation. The new equation. So we solve that new equation. That gets us one of our unknowns. And our last step, step 4, use the answer from 3 in either of the original equations. So we can use the answer from 3 in either of the original equations. So we combined our equations together. We had a value eliminate. We solved for one of our unknowns. Now we can use that solution to eliminate that unknown from one of the other two equations, one of the original two equations. We call this back substitution, where we go back to our original equations and substitute in what we found. So it doesn't really matter which equation you go to. So because I like positives, I'm going to go with x plus y equals 5. Be careful here. Big possibility for errors here. If you copy down the equation wrong and you plug things in to that wrong equation, you will get wrong answers. So make sure if you're copying equations down, you copy down exactly the right one. So I'm going to substitute in x equals 3. So I have 3 plus y equals 5. We now have another equation in one unknown. So we can solve that equation. So I'm doing it again, going to my answer before I do the solution. So subtract 3 from both sides and y equals 2. So when we solve two equations in two unknowns, we have to manipulate the equations a little bit so that we can combine them together and eliminate one unknown. That's a lot of work up front, but once you do that and eliminate one unknown, then you've basically got two simpler equations to solve. And we solve those two equations and it gives us our answer. The answer to any simultaneous equations usually is going to be 2 values. So our answer here is x equals 3, y equals 2. It's a point in space where these two lines, or at least in a plane, where these two lines cross. So that's the basic procedure. Most of the work is up in basically step 1 and 2, is figuring out how you're going to set up the equations to eliminate one of the unknowns. And there are lots of different ways to do this. You can use any method you want. You can set things up any way you want, as long as when you combine these equations together, you lose one of your unknowns. Maybe you wanted to eliminate the x in this one. You can make that work. And it's one of those things that is at the same time a benefit and something that's kind of a problem. It's kind of a pain. Here we have lots of different ways to do this. So what you do and what your neighbor does, or what your friend in the class does, may be different, but you'll get to the same answer. There's nothing in the procedure that you follow that should ever give you a different answer in the end. There's only one answer to this set of equations. So that's the basic process, and we'll do a couple more examples of that to get the idea down. We'll do a couple more simple ones, and then we'll do one that's a little more realistic, one that's got some kind of ugly numbers in it, and I'll show you how you can really deal with those kinds of equations. Anyone have any questions on the basic procedure here?
No.
All right, so let me go back to the slides here. There we go. So this is all detailed out in the notes, by the way, so you can see those in the in there. I've written out basically the procedure for solving this one set of equations to give you a little refresher on it if you have to come back and look at it again. But we combine the equations together, we solve that, and then we plug it back in to either of the two equations, solve for the remaining unknown. So let's try another one here. A little different, a little more sophisticated. So here we've got 3x plus 5y equals 100, and x plus 5y equals 50. So let's see how that one works. So let me write those down and then we'll switch over. So 3x plus 5y equals 100, and x plus 5y equals 50. And by the way, if you've done this before, if you have your favorite method of solving simultaneous equations, whether you know things like Cramer's rule or you do matrix methods or anything like that, go with whatever works, whatever's comfortable to you, whatever you know. Feel free to use that. And as long as you get to the right answer in the end. This is engineering. We care about performance. We care about making sure we get the correct answer. So let's switch over here, and there we are. So 3x plus 5y equals 100, and x plus 5y equals 50. So our first step was to look for an unknown that has a sign difference in the two equations. There's no unknown with a sign difference here. So we're going to have to make one. And the way we make one is essentially by flipping the signs on every term in the equation. Remember that as long as we do the same thing to both sides, we're not going to change the equation. We're just going to make it look different. So there are a couple different ways to go on this one, but I might say if I take this lower equation here, the second equation, if I basically multiply both sides by -1, that's effectively what you're doing when you just change all the signs in every term. I'm going to have a different looking equation. So if I multiply every term by -1, this is going to be -x minus 5y equals -50. Same equation. If you're not quite sure of that, make sure you, if you're watching this on the video, pause it and think about it for a while until it does make sense to you. But essentially, if you flip the signs on every single term, you end up with exactly the same equation. You're really just multiplying both sides by -1. I'm not going to do anything to the top equation. So on the bottom equation, I just multiply by -1. On the top equation, I'm not going to do anything. I'm going to leave it as it sits. 3x plus 5y equals 100. So in our step 1 here, we had to look for an unknown that has a sign difference and target that one for elimination. If there is no sign difference, make one by multiplying one of the two equations by -1, by flipping the signs of every term. Step 2 was to make the coefficients of the unknown targeted for elimination the same. And again, there's a little bit of art to this where you can look ahead a little bit and think about what's going to be easier, what's going to be harder. If we look at the y's here, the y's already have the same coefficient. So it really wouldn't be useful to me to try to make the bottom equation, the second equation, -3x. If I did that, I'd be creating more work for myself. All I need is one of the two unknowns to have the same coefficient, but different signs. And y's already got that here. So we can go on to step 3, which was to add the two equations together. If we add the two equations together, on the right side, we've got 100 minus 50. So that's just 50. On the left side, we've got 3x minus x. That's 2x. And 5y minus 5y, that's 0. So we've eliminated successfully y. And we're left with one equation and one unknown. 2x equals 50, and that we can pretty easily solve. Divide both sides by 2, and x equals 25. Don't stop there. One of the biggest point losses I see typically in simultaneous equation problems and just the basic math problem is people stopping short. They get one of their values and they just stop. You got to have two values because you've got two unknowns. So, excuse me. So x equals 25. Yes, you got a result. Don't get too excited and move on to the next problem. Go back, finish the problem up. We now need to take that and plug it into either of the two equations. And since, again, mathematically, I try to be pretty lazy, so I'm going to pick the equation that looks like it's going to be less work for me. And looks like the second equation looks good to me. I always go back to the originals because maybe I made a mistake in setting these things up and all that. If I made a mistake down here and then I carry that back into my original equations, I'm more likely to catch that mistake. If I go back to equations I've messed up and I plug things back in, I might not catch the mistake. So I always go back to my originals. So let's go to the second equation here. We've got x plus 5y equals 50. Oops, sorry about that. So x plus 5y equals 50. We'll plug in 25 for x. So let me write the equation down. X plus 5y equals 50. Plug in 25. So we've got 25 plus 5y equals 50. Can solve that one using our skills from Monday night. Subtract both 25 from both sides. We've got 5y equals 25. And now we can solve, divide both sides by 5, and y equals 5. So it looks like our answer here is x equals 25, y equals 5. If you wanted to be sure that the equation was, that your answer is right, go back to whichever equation you didn't use to find your missing value and plug it in. Plug your answers in to see if it works. So it's a good check. So let's go ahead and do that just to show that it works. I've got 3x plus 5y equals 100. And I always use the other equation because maybe I screwed something up here in my solution. If I go back to the same equation I used to solve and I make the same mistake, I might end up I might not end up catching it. So I always go back to the other equation. So we've got 3 times 25 plus 5 times 5. I want to see if that's 100. We've got 75 plus 25. That looks like 100. So that checks out. So that's simultaneous equations. Any questions on that one? All right. So let's try another one here that looks a little bit more complex. One where we're going to have to force some issues here. So let's try 3x plus 2y equals 10, and let's say 6x plus 8y equals 4. Now I'm just making these up. We'll be able to get a solution. I'm not guaranteeing the solution is going to look nice. Realistically, more often than not, when we work on practical problems, we don't get nice answers. So we have to round. We end up with decimals. This is real stuff. So it's not toy math problems from math class where the answers are all whole numbers and everything always works out perfectly. So let's take a look at this one here. Now, there is no built-in sign difference on these, so I'm going to have to make one. And so I'm going to flip the signs on one of these two equations. And I think just for fun, I'm going to flip the signs on the first one. So I'll multiply by -1 there. That'll make it -3x minus 2y equals a -10. Same equation, just all the signs are flipped. I'm going to leave the bottom equation alone. So I've got 6x plus 8y equals 4. So we've got a sign difference now. And in fact, we've got a sign difference in both of our unknowns. So it's really up to figuring out which one do we want to eliminate. Well, we eliminated, let's see, we eliminated y in the last problem. So let's eliminate x in this one. The next step in solving simultaneous equations is to make the coefficients the same. Well, we don't have coefficients that are the same. We've got a -3 on the x from the first equation, and we've got a +6 on the x from the second equation. We need to force those to be the same. We can do that though. We can borrow an idea from what we did up here. Here we changed the equation by multiplying each term by -1. That works for any number. It doesn't matter what number we pick. As long as we multiply every term by the same number, it won't change the equation. It'll change what it looks like. It'll change the numbers that the equation's written down with, but it won't change what the equation represents. And that's what's really important. So the way I'd look at it here is I'd say, well, I've got a -3 here. I want that to be a -6. Well, I can make a -3 into a -6 by multiplying by 2. So I would take my first equation. So I'm going to write this down on a second line here. I'd normally go across the whiteboard on it here, but I'm going to rewrite the equations as we've got them at this point. And again, there are multiple ways to do it. If you're taking a different path on it, as long as you're getting to the same answer, it's fine with me. I'm just showing you one possibility, how I'd probably do it. So we're going to transform these equations again. Again, I'm going to leave the bottom one alone. So it's just going to be 6x plus 8y equals 4. The upper equation, I'm going to multiply by 2. I'm going to multiply each term by 2. So -3x will become a -6x. -2y will become a -4y. And -10 will become a -20. And as you get more skilled at this, if you do these a lot, you'd probably bundle this up into one step where you'd say, well, I can make my sign difference and I can make the coefficients the same if I just multiplied each term by -2. But to start with and get a little more practice with it helps to kind of do it as separate steps. So now we've gotten we've got our sign difference now, and we've got our coefficients on x, the same size, but different signs. That's when we can add these equations together. We can move on into our next step and add the equations together. So if we add the equations together on the right, we've got -20 plus 4, that's a -16. And we add on the left, -6x plus +6x is 0. We've got -4y plus 8y, that's a +4y. Now we can solve that, divide both sides by 4, and it looks like y is -4. So we've successfully eliminated x, and we've gotten our and half of our answer. We've got a value for y. Now we can go ahead and back substitute. We can go back to either of the two equations. And I'm going to pick the top equation just because it deals with smaller numbers, less to multiply, all of that. So we've got 3x plus 2y equals 10. I'm going to plug in y as -4. So I've got 3x plus 2 times -4 equals 10. And just one step at a time, going through and solving it. -2 times 4 is -4 times 2 is -8 equals 10. Add 8 to both sides. And we get 3x equals 18. Divide both sides by 3. and it looks like x equals 6. So it looks like we've got a solution. We've got a candidate solution here, x equals 6, y equals -4. And to check that, we can go to the other equation that we didn't use. We didn't solve for x using the bottom equation, so I'm going to use that one for my check. So let's see if it works out here. 6 times 6 plus 8 times 4. That should equal 4 plus 8 times, -4. See, I lose negative signs. So keep an eye on me. Let me know if I skip something. 6 times 6, 36, plus 8 times -4, -32. That looks like 4. So we've got the right answer. So x equals 6, y equals -4. Making sense how that works? All right, so let's do one more before we go on and review a little bit of trig. This time, I want to write one up here that involves a little bit more realistic numbers. When you're dealing with whole number coefficients, you can do like what we did here. You can find integers, find whole numbers that you can multiply the equations by to match up the coefficients. But when you've got decimal coefficients, that's not always easy. And in fact, it's not always possible. So you might not necessarily find a number that you could multiply by, but multiplication isn't required. You could also do division. And that's the method I tend to use when I've got kind of ugly numbers that I just want to get rid of and eliminate one of the unknowns. So let's see how that would work. And this will be how it'll likely work if these come up in any kind of practical problem we're dealing with. So let's write up an equation. Let's say we've got 0.5x plus, let's say 0.866 y equals 12. And let's say we've got 0.7071 x plus 0.7071 y equals 4. Now, for those of you who know a little bit of trig, those numbers might look familiar to you. Certainly for those of you who have been through electricity, I know 0.7071 looks familiar to you. That whole RMS thing happens to come up to be the same thing as the sine or the cosine of 45 degrees. So this is realistic. Typically our coefficients are sines and cosines of angles in practical problems. And there's no matching these up. We've got a built-in sign difference here between x in the first and x in the second equation, but turning 0.5 into 0.7071 or turning 0.7071 into 0.5 or turning them both into some other number is going to involve a lot of work. So here's what I do with it. The easiest thing I can turn that coefficient into is 1 by dividing the coefficient out. It's a legal move as long as you do the same thing to each term. So in the first equation, what I'm going to do here is I'm going to divide each term by 0.5. If I divide each term by 0.5, I'll end up with an equation that has a nice coefficient for x, and I'm targeting x for elimination here because it's already got a sign difference. If there was no sign difference, then I'd flip the signs on one of the equations and then figure out a variable from there. but here I'm going to eliminate x because it's already got a sign difference there. I just have to match up the coefficients. When you divide through, you're going to get a nice coefficient for x. It's going to be 1. The other coefficients may not be as nice, but we don't really care so much about those yet. So we want to make that coefficient in front of x 1. So if I divide 0.5x by 0.5, I'm going to get x. If I divide 0.866 by 0.5, I'm going to get, I should get 1.73, I think. 0.866 divided by 0.5. Yep, 1.732. So we get 1.732y. And then dividing 12 by 0.5. Hopefully you don't need your calculator for that. That's 24. So that's our new first equation. Ugly coefficient for y, not so bad for the whole number side here, or for the right-hand side, but nice coefficient on x, just a positive 1. For the second equation, I'm going to divide the equation through by the coefficient of x. So I have 0.7071. I'm going to leave the negative. I don't want to divide through by a negative because I want that built-in sign difference. Sorry. All right, so I'm going to divide through the second equation by the coefficient of x. So I'm going to divide by 0.7071. So I'm going to divide each term by that. Unfortunately, the way I set this one up, we're going to end up with with nice coefficients here, but in realistic problems, it won't necessarily come out that way. So dividing the first equation, or first term by 0.7071, we get negative 1x, or just negative x. Dividing 0.7071y by 0.7071, we just get 1y. Here's some ugliness. We've got 4 divided by 0.7071. So we've got 0.7071 and 4. That gives us, looks like 5.65. I'm going to round there to 7. Yep. So we get an ugly number there, but ugly numbers, we got to get used to working with them. We've got our built-in sign difference now, and we've got our coefficient matched up. Everything else is ugly, but we're going to be able to eliminate x pretty easily. And there are lots of other methods of doing this, but I think this is the one that, at least for me, works out to be the fastest. So now we can add the equations together. X plus a negative x is 0, so those eliminate. Those are gone. 1.732y plus y is 2.732y. Don't get thrown by decimal coefficients. It all works the same way as with whole numbers. You just add them up. And then we've got 24 plus 5.657. That's going to be 29.657. Now, although it looks ugly, we solve it the same way. Divide out the coefficient for y, divide both sides, and you'll get your answer. So we divide both sides by 2.732. So we have 29.657 divided by 2.732. That gives us 10.855. So that's our value for y, 10.855. We're not done. We still need to come up with a value for x, but we do that by back substitution. So I'm going to go back to my top equation here because it looks like less work. So I'll go over here on that one. We have 0.5x plus 0.866 times 10.855 equals 12. And we'll run the numbers through on this one. 0.866 times 10.855, 9.400. And that equals 12. Subtract the 9.4 from both sides. So we have 12 minus 9.4. So we have our 2.6 there. So 2.6 and 0.5x. Solution's the same with decimal coefficients, just divide both sides by the coefficient. And x will be 5.2. So there we go. A little uglier, but hopefully not too difficult. Not for two equations and two unknowns anyway. I think you might be able to see that if this was 3 equations and 3 unknowns or more than that, it would get really messy really quickly. And that's about when we bring in calculators or programs like MATLAB and things like that. If you're familiar with MATLAB or have heard the term, this is basically all MATLAB does. MATLAB's all about solving linear equations, solving simultaneous equations. So we get some ugly numbers, but it works. This would be the kind of problem we would likely end up solving in practice. Any questions on that one? All right, well, if you get stuck trying it on your own, trying it on the homework, go back to the video, try and watch that through again, so see if you can see if it helps to go through. And of course, if you're stuck, feel free to contact me and we'll try to figure it out. So let's see, let's go back to the notes. All right, so let's take a look at some right triangle geometry here. This is the last skill we need, last basic math skill we need in order to be able to solve practical problems in this class. So some terminology first. When we deal with a right triangle, we've got 3 sides. The longest side, the side right here, we call the hypotenuse. We've got our legs. The hypotenuse stands on the legs. The legs are the 2 sides that touch the 90-degree angle. And those are the terms we use for them. The letters A, B, and C are arbitrary. In fact, we'll call them different names depending on the situation. But A, B, and C are traditional, with A and B being the legs and C being the hypotenuse. Now, some facts about right triangles, some useful things to know, is that when we add up all the angles in a right triangle, we've got a 90-degree angle and 2 acute angles. We have a total sum of all the angles of 180 degrees. 90 of that's tied up in that corner, so the other 90 has to be split between the other 2 angles. So that means that if we have a right triangle and we know one of these 2 acute angles, we automatically know the other one. Now, in a math class, you might use that to figure out some value or to actually do calculations with. In practice, in engineering, to minimize errors, we try our best to use the information that's given to us, rather than trying to calculate other information that we will then go and do our calculations on. Because if we screw up that intermediate calculation, everything's going to be messed up from the beginning. So we typically will rely on whatever angle information's given to us. But it's useful to know that we have these 2 complementary angles, 2 angles that add up to 90 degrees. So that's one important fact about triangles. The hypotenuse, always the longest side. So that serves as a useful check when you're working with triangles. If you do calculations and you figure out the length of that long side versus the length of the other sides, and it's not as long as the legs, you've got something messed up. The hypotenuse has always got to be longer than the other two sides. And then we had that formalized, the physical relationship between the size of the legs and the size of the hypotenuse in what we call the Pythagorean theorem. The Pythagorean theorem only works for right triangles. There are corrections to it for non-right triangles. In fact, if you've been through some more advanced math and you know something called the law of cosines, the law of cosines is basically the Pythagorean theorem, but for a non-right triangle. The right triangle, Pythagorean theorem, has its simplest form, and it says that if we take the lengths of the two legs, we square them and then add them together, we get the length of the third side, the hypotenuse, squared. So we say that the squares of the legs, the sum of the squares of the legs, equals the square of the hypotenuse. So we're able to figure out, if we know 2 out of 3 of the sides, we can figure out the third side. So the Pythagorean theorem lets us figure out a missing side. Now, we used this back in the A&P program, and we learned about Pythagorean triples and all that, 3, 4, 5 triangles and all that. We don't really need that much here. In fact, the basic application of the Pythagorean theorem for our purposes will be to calculate the length of a hypotenuse. We're going to learn that when we do calculations in a lot of the problems that we solve, we tend to find the lengths of the legs. The legs are the easier things to find. And so we do our calculations on the legs. But in the end, at the end of our problem, we usually want to know what the length of the hypotenuse is. And so if we know the legs, we can square them, add them together, and then take the square root. That'll give us the length of the hypotenuse. That'll be about the only application practically that we'll do of the Pythagorean theorem. Now the homework that we've got is essentially just practicing on math skills. So you can expect to do a little bit more mathy type problems for that. But in practice, it's only ever one equation or one procedure. We are finding the hypotenuse from the legs. So that's the Pythagorean theorem. So it lets us find one of the two sides as long as one of the sides as long as we know the other two. But the question then comes up: what happens if we don't know the two sides, or 2 out of 3 of the sides? We only know one of the sides. Say we only know the hypotenuse, which is the typical problem. The typical problem is we know the hypotenuse and we want to know what the legs are. Well, short answer is if all we know is the hypotenuse and nothing else, we're basically done. We can't do anything. That'd be kind of the math class answer for it, is we're done. We're screwed. We can't do it. We have only one piece of information. Now, of course, in practice in engineering, that just tells us we need more information. We got to go measure something. And typically what we need to measure is going to be an angle. If we know the length of the hypotenuse and we know one of the acute angles, we can find the legs. And that's what trigonometry is all about. So if we know one side, typically the hypotenuse, and one of the acute angles, we can find the remaining sides. And that's what trig's all about. So trig, the measurement of triangles, lets us figure out everything we want to know, all the sides, all the angles, based on the triangle, on the information we're given. We do this, and I went into some more of the philosophical discussion about it, I suppose, in the first semester in the A&P program. The basic review on that is we have these three ratios. We give them names. We call them sine, cosine, and tangent. And those ratios are the values that are the ratios the sides have to have, certain pairs of sides have to have if we have a certain acute angle. If we build a right triangle with an angle of 30 degrees in it, the sides are only going to have certain ratios to each other. They may have different physical sizes, but their proportions will be the same. If I take the ratio of one of the legs to the hypotenuse or the other leg to the hypotenuse, it's always going to come out the same for every triangle that's got 30-degree angles in it. That's the value of trigonometry. It lets us remove the scale so that we get all the triangles in the world with 30-degree angles in it condensed down to one. And we can do all the math based on that. So we have our three ratios. And as long as you know the definitions of the ratios, just like solving ratio problems, if you have the definition and you know the value, you can find missing pieces. You can solve the equations. So we had our three trig functions. We had sine, cosine, and tangent. The definitions depend on naming the legs on the triangle. So let's go back to the picture here. The way we name the legs is based on how or which angle we choose to work with. And which angle we choose to work with depends on what information we're given. So if I'm given this angle down here in the right-hand corner, we're going to give the legs different names. The hypotenuse is always the hypotenuse, but we'll give the legs different names. The leg that doesn't touch the angle we're working with, that is opposite the angle. So we call that the opposite side. The opposite side doesn't touch the angle that we're working with. The side that does touch the angle that's not the hypotenuse, we call that side the adjacent side. Adjacent's a fancy way of saying next to. So we pick an angle to work with. That names the sides: opposite, adjacent, and hypotenuse. And the ratios, sine, cosine, and tangent, are defined in terms of opposite, adjacent, and hypotenuse. Make sure once you pick an angle to work with, don't change it. If this is a 30-degree angle, for example, and you decide, well, I'm going to work with a 30-degree angle, then halfway through the problem, you switch to working with this 60-degree angle up here, well, then you're going to end up crossing up your names. Opposite's going to be adjacent, and adjacent's going to be opposite, and things are going to get confused. Start at the beginning of the problem, pick an angle, and work with it. Don't change it once you've made that selection, because it changes the names. So let's look at our ratios. We have the sine. The sine is the ratio of the opposite to the hypotenuse. So we take the side that doesn't touch the angle and we put it over the hypotenuse. So sine is the ratio of opposite to hypotenuse. That little parentheses with the funny looking zero with a line through it, that zero is an angle Greek letter, the Greek letter theta, one of the common symbols we use to stand in for angles. And so the opposite over the hypotenuse, that's the definition for sine. Cosine is the adjacent over the hypotenuse. Looks a lot like sine, but it deals with the adjacent instead of the opposite side. In fact, the biggest, I suppose, tip I can give you at this point to making sure you're going to use trig effectively in this class and lots of others is to burn into your brain: sine goes with opposite, cosine goes with adjacent. When we do practical calculations like the ones we'll be starting on Monday, we start out with a hypotenuse and an angle. We want to know the opposite and the adjacent sides out of that. Sine gives us opposite, cosine gives us adjacent. That association will always hold. If you've dealt with this before in other classes, and you're used to thinking of things like X going with cosine and Y going with sine, break yourself of that, because that's not always going to be the case. It depends on what reference we use for our angle. Sine going with opposite, cosine going with adjacent, that always works. What we call X and what we call Y can depend on the problem. So get used to thinking cosine adjacent, sine opposite. And that'll help you out quite a bit in solving problems. And then we got the tangent. Practically speaking, we don't use the tangent directly. We tend to use the tangent backward. We tend to use the tangent when we want to figure out the angle and not when we want to figure out a side. And we'll see how that works here in a bit. But tangent is defined as opposite to adjacent. So it's our opposite side over our adjacent side. It's the only one of the trig functions that doesn't involve the hypotenuse. So those are our three trig functions. The little trig function mnemonic, SOHCAHTOA. So if you can remember how to spell that, SOHCAHTOA, sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, and tangents opposite over adjacent. That gives you your definitions. And unlike the in the A&P program where I gave you all the equations, I don't give you any equations on the exams here. Now, don't panic just yet. What I do for the exams is you're allowed to bring in to the exam a 4-inch by 6-inch index card with any information you want to put on it at all. In fact, you get 1 for the first exam, you get 2 for the second exam, 3 for the third exam, and 4 for the final. So it's worth keeping those. So I don't put any extra information on the exam. I don't give you things like that, except for material constants where I don't expect you to go and write down the whole reference book. But equations, things like that, I won't be giving you. It'll be up to you to have those definitions with you if you need them. So let's try a couple examples here. So let's start out with kind of the classic problem that we would be doing in this class. In this class, we typically use trig to take a hypotenuse and an angle and break it up into the sides, into the legs. So let's set up a problem like that. Let's say we've got a triangle that looks something like this. We'll make the hypotenuse 10, and I'll make the angle down here 30 degrees. Now this is assumed to be a right triangle. It has to be because we can't do the problem otherwise. We need to have a right triangle here. We don't have the mathematical tools to deal with it otherwise. So even though I might not always draw the little box down there, it's safe to assume that it's a right triangle. Now what we want to know are the other two sides. We can go and find the missing angle here, but we're not going to use it for anything. Since all three angles have to add up to 90, the acute add up to 180, the acute angles have to add up to 90, so this must be 60. So we can kind of write that up here, but I'm not going to use it for anything. I'm going to pound my stake in the sand here and say, I'm going to use 30 degrees. Once I decide to use 30 degrees, that names the legs for me. This will be my opposite side, which will abbreviate OPP. We'll call this side the adjacent side, since it's next to the 30-degree angle. And just for completeness, we'll label the hypotenuse HYP. So in this situation, when you know the hypotenuse and the angle, you're always going to be using sine and cosine. Sine will give you opposite, cosine will give you adjacent. If you weren't sure, you could go and write down the ratios. Sine of 30 would be the opposite over the hypotenuse. Cosine of 30 would be the adjacent over the hypotenuse. And the tangent of 30 would be the opposite over the adjacent. Those are our definitions of our ratios. We can fill in what we know. The only side we know is the hypotenuse. So we've got a hypotenuse of 10. We don't know opposite, or we don't know adjacent. So tangent we can't really use. It's missing too many pieces. Tangent of 30 has a value, but we can't use that to figure out what the opposite and the adjacent side would be. Yes, in principle, you can go and solve one of these two and then go use the tangent, but that's risky. Because if you made a mistake up here, and then you carry that mistake down into here, you have no chance of getting the other one right. These two are independent of each other. I could screw up the opposite, but still get the right answer for adjacent, because one doesn't depend on the other. It also minimizes round off error, because if you round off your answer for opposite, and then you use that rounded off answer here to figure out adjacent's going to be a little more rounded. It's going to have a little more error built into it. So I always go in these problems when I know the hypotenuse and an angle. Sine and cosine are the go-to. Sine gives you opposite, cosine gives you adjacent. So how do we use it? Well, we have to know the values of our trig functions. So if you have your calculator with you, let's check that out. If you don't have your calculator, make sure you check it out later. Come back to this point in the video and make sure the numbers work out, because calculators can be configured to use all sorts of different numbers or different units for angles. We're using degrees here. Your calculator might be set up for radians or for some other angle unit. And if it's set up for some angle unit other than degrees, you're going to get weird answers. So make sure it's set up for degrees. So let's deal with sine first here. So we've got sine of 30 equals my opposite side over 10. Well, if we go to the calculator and key in sine of 30, we should get 0.5. So 0.5 is opposite over 10. Well, that's just a ratio problem. It's a proportion problem. We can solve that by cross multiplying. Opposite times 1's opposite. 0.5 times 10 is 5. So our opposite side appears to be 5. We can do the same thing for cosine. For the adjacent side, we have cosine of 30 is adjacent over 10. If we go to the calculator and let's practice some sig fig work from last time. Let's keep 5 sig figs here. So if I go to my calculator and I key in cosine of 30, I'm not going to get as nice of a number as 0.5. I'm going to get 0.86603 to 5 sig figs. Now that's adjacent over 10. So if I cross multiply, it looks like my adjacent side is 8.6603. And there we've got the triangle. Now we could certainly check this with the Pythagorean theorem. If you went to your calculator and keyed in 5 squared and 8.6603 squared, should come out to be 100. 2 within 5, maybe 4 sig figs, depending on how much round off we did. Since we only rounded off at one step here, I'd expect it to match to 5 sig figs. That's something that you're going to be doing. You're going to do the same exact problem probably a good 200 times throughout the rest of this class. You're going to do it for almost every problem we solve, every homework problem, every exam problem. If it involves a force, you're going to use it, because this is how we break up a force into horizontal and vertical pieces. It's a right triangle. The hypotenuse is how much force we've got at some direction. The opposite and the adjacent sides are how much pull or push we've got in the horizontal and vertical directions. So this kind of problem you're going to do over and over and over again. So don't worry if you're a little sketchy on it right now. You're maybe not feeling so good about it just yet. Practice this part. Make sure this makes sense. What was done here, go back and review it if you have to. And we don't worry too much because we will be doing these over and over again. I'll be doing many more examples where the same math will be involved. It'll just be worked on a force, not on the lengths of the sides of a triangle. So that's about the most common application of trig that we've got. Any questions on this example?
Nope.
All right. Well, let's do one other common example here. I don't think I have one like this on the homework, but it's about the most common situation we run into with solving problems. Normally, when we are using trig the way we just did, we've got the hypotenuse and we've got an angle. On the other side of the problem, after we've done our calculations, we end up building another triangle. Kind of the final step in solving our problems is building another right triangle, but this time we know the legs and we want to find out the hypotenuse and the angle. So let's make up some numbers here. Let's say we've got 3 and 4 for those legs, and we want to know the hypotenuse and that angle there. And since this angle is the one I want, that's going to name my sides. The 3 is my opposite side, and the 4 is my adjacent side. So in the previous problem, we knew the hypotenuse and the angle, and we leaned on sine and cosine to turn those into the legs, to figure out what the legs were. So we needed 2 tools to do that, one for each piece of information. Here we're trying to take the legs and figure out 2 pieces of information, the hypotenuse and the angle. And we're going to need 2 tools to do that for us. The first tool is the Pythagorean theorem. When we know 2 of the sides and we're missing 1, the Pythagorean theorem is the go-to. And I'm going to write the Pythagorean theorem down here in terms of opposite, adjacent, and hypotenuse. Hypotenuse squared is the opposite squared plus the adjacent squared. Or if you look ahead a little bit and solve this, if you take the square root of both sides, we can say that the hypotenuse is the square root of the opposite squared plus the adjacent squared. And remember your order of operations here. When you're using this, you'd have to apply your powers first, then do everything underneath this root, get it down to a number. The last step is taking the square root. So let's use it. Opposite side's 3, so I've got 3 squared. Adjacent side is 4, so I've got 4 squared. I'm going to take the square root of that. 3 squared is 9. 4 squared is 16. That's the square root of 25, which is 5. Now, I admit I knew that going in, since this is a Pythagorean triple. The 3, 4, 5 triangle is probably the most common length sides of triangles that people use, because the math does work out fairly easily, at least for the legs and the hypotenuse. It's not so great for the angle, but it's fine for the legs. So we figured out our hypotenuse is 5. So to go from the legs to the hypotenuse, we use the Pythagorean theorem. We still need this angle. Now that I have all 3 sides, in principle, I could use any of the trig functions. When you know the value of a trig function. For example, if I know the sine of some angle is 0.5, we can use what are called the inverse trig functions. We can ask our calculator to tell us what angle has a sine of 0.5, a sine that has a value of 0.5. If you look at the sine button on your calculator, there's usually a second function to that sine button that has sine with a little -1. That means inverse sine. If you key into your calculator 0.5 and you hit that sine -1 button, it should tell you that the angle is 30 degrees. That's the only angle between 0 and 90 anyway that has 0.5 for a sine value. We can find these values, since these values are just ratios of the sides. If we know the sides, we can take the ratios. Opposite over hypotenuse, 3/5. Adjacent over hypotenuse, 4/5. Or opposite over adjacent, 3/4. We could use any of those at this point, but the one that I'm going to encourage you to use the most is tangent, because we were given the 3 and the 4. We were given the opposite and the adjacent sides. So we should use a trig function that only involves the opposite and the adjacent sides. Sine and cosine both involve the hypotenuse. So I'm going to use the tangent. Tangent of some angle, my unknown angle, is opposite over adjacent is 3/4, or 0.75. So we can go to the calculator and ask, what angle has a tangent of 0.75? And you do that by keying in 0.75 and hitting your inverse tangent key, usually shift of tangent, or however you have to key it into your calculator. Different calculators have different syntax to do that. On mine, I have to enter the ratio first, then hit the trig value. And when I do that, again, I'll round to 5 sig figs. My angle is 36.870 degrees. Don't forget that degrees sign, by the way. That is kind of like the unit for the angles, so it's important to write it in there. So 36.870, remember those trailing zeros after the decimal point count. So that's definitely 5 sig figs. So the 345 triangle has kind of an ugly angle to it, 36.870. We can, and these are the two tools that we use when we've got the legs and we want the hypotenuse and the angle. We use the Pythagorean theorem to get the hypotenuse. We use the inverse tangent to get the angle. So we figure out what the ratio is for the tangent. We hit that inverse tangent key and it gives us our angle. Anyone have any difficulties getting the numbers involved here? Everyone's calculator working correctly?
Yep.
All right, if you're trying that out, make sure that's working. So those are basically the trig skills we're going to need. Now you've got a few other problems to practice on the exam, on the homework assignment, but you should have all the tools to do the homework assignment at this point. When we come back on Monday, I'll ask if anyone has any questions on the homework, but if anything comes up that's tricky, we'll discuss it a little bit in class. And of course, Wednesday night next week, if there's any particular problem you want to see worked out, make sure you bring it to class, and we'll try and work it out. So let's see here. So next time, we're going to start getting into the real meat of the class. We've got the mathematical preliminaries done. We've got every math tool we're going to need. There's nothing else that we need for this class. There's nothing hiding, no other techniques or or principles or equations I have to teach you or anything like that. Well, there are some equations, but there are no other. You've met all the techniques you're going to need to deal with those equations. So the math itself doesn't get any harder. It's now all application of it, and we're going to start that application with vectors. We'll look at what we call scalars and vectors, and we'll get a little bit of that terminology down. We'll look at coordinate systems, and then we will see how we can do some math with vectors. We'll do part one, which is what we call graphical vector math, how we can add and subtract and multiply with vectors when we draw them out. On Wednesday next week, we'll see our real application of trig by adding and subtracting vectors mathematically. So we'll see how those all work and how that fits in. Anyone have any questions?
Nope.
All right. Well, I'm going to stop the video here, but if anyone has any other questions or wants to see any other problems worked out, maybe feeling a little bit iffy with trig and all that, I'm online here till 7:30. So if there's anything that you want to have worked out, feel free to stay on the line. Otherwise, have a good weekend, and I will see you Monday night.
All right. Take care.
Have a good night.